Bless.
Thank you.
All right. All right. What is root finding about? Gardening?
Finding a root.
Finding a root? Which root? Of what?
Of a number.
Of a number. What is the root of a number?
Polynomial.
Polynomial, so let's expand polynomial a little bit. A function. Okay? So I can come up with a function, and I am wondering so function is a function that depends on x, let's say, and then I can wonder which x would get 0 out of this function. Okay? So sometimes we call them zeros as well, and then the result, this root is a number. Okay? So it's a number that basically zeroes out a function. Now, that sounds really esoteric and mathematical, but ultimately a lot of problems that we come up with that need a solution come in a form that, some function that depends on whatever parameters I have in my model that are modeling some situation is equal to a 0. Quite frankly, if that function is equal to 10,000, it's the same thing if I'm looking for, because then I'm just going to change my function to be that original function minus 10,000, and then I'm formulating it in terms of finding a 0. So mathematically, we are calling it roots and finding a 0, but basically a lot of problems can be formulated in this sort of this conceptual form: f of x is equal to 0, and then I'm looking for for x's that do that. So this is actually our first topic that is actual numerical method. Before that, we were just kind of gathering our toolbox so that we can actually now have all of the tools and knowledge base to go in and actually solve a problem. So MATLAB fundamentals, programming, debugging, and errors, these were all sort of like tools that I use to actually solve problems. And so the rest of the chapters are essentially numerical methods that tackle certain areas. So here's one example. I don't know, how many of you are legal to drink? Not so many, so maybe not so interesting example yet, but it might come in handy later. So there's a martini glass, there's a red wine glass, and here's an example. If my martini glass is filled to 6 centimeter depth, it contains 216 times pi divided by 3 of wine. So that's a certain volume in milliliters. How deep must you fill the wine glass, okay, to ensure that it actually has the same amount of wine as you have for cocktail? And one of these days, once you're legal to drink, and if you actually decide to drink in life in general, you might be wondering yourself this question in the restaurant. Maybe not. So it's just a question after all. So then we are coming up with a model. So the procedure is like, okay, how do I think through this process, regardless of what it is actually talking about? So, okay, my red wine glass, it looks like a sphere cap flipped over. Okay, so that's a good model for me to use because I know a whole lot of equations that involve spheres and sphere caps. Okay? So my volume of a sphere cap, then you'll go look into your geometry book. You can either derive it quickly or you can remember where to look it up. You look it up and say, this volume, if I have a sphere cap that is sort of h is its height, and I have this arm here whose length is a, then there's a little bit of Pythagoras theorem and so forth that tells you that the volume of this cap is pi over 6 times h times 3a squared plus h squared. Now, I can basically make this, since I know the radius of my sphere cap, that's something that is given with the glass that I'm working with, I can use that in Pythagorean theorem to actually just figure out what a squared is in terms of r and h. So that's a little bit of geometry. I plug it in, and I also use that my radius is 7 because my wine glass is given to me. I will get what this volume, okay, is. Now, I am wondering, okay, so since I'm looking for this, for where this volume actually fills, so now this volume is actually a function of H, okay? And depending how much I fill up my glass, I fill up my glass up to H, depending on that my volume changes. Okay? So basically the result, I'm looking for H, where this formula is equal to the volume I'm after, which is pi times 216 over 3. Now you can see actually why I gave myself a volume that has a pi inside so that things cancel. So my modeling, so there was a little bit of modeling in the process, and you kind of had to do that. Come up, is the glass perfectly spherical? Probably not, but it's a good model for it. Okay, it's close enough. So basically, once you actually do that, so I am looking, and I will put R is equal to 7. I'm looking for, and I will put this on the other side to actually have a formula that says f of h is equal to 0. So I'm formulating or looking for h that says that 7h squared minus h cubed over 3 minus 216 over 3 has to be equal to 0. Okay. So are we clear about the process? One part of this later on will be like, I will pose a question that has a physical problem, and you will have to formulate it in this f of h is equal to 0 or f of x is equal to 0, because that's how all of our methods will be working for. That's the problem they will be working for. Okay. So a lot of different problems will just have to be put in this form so I can actually start using. Now there's all kinds of different problems, and I'm going to first exemplify a number of them and how varied they can be. Another one is quite a famous and used one, and once you get through your thermo, you will love it. It's Peng-Robinson equation of state. Those who are in thermodynamics are already smiling. Have you worked with it yet? Yeah. So now our simplest gas law is ideal gas law. Okay? Ideal gas law says that pressure times molar volume is equal to R. R is a gas constant times temperature. So it's a relatively simple relationship between pressure, volume, and temperature. Great. Now, ideal gas is really, they formally think about gases as these very rarefied molecules that are kind of thought of as spherical. If they do collide, they have these perfect elastic collisions. There's this like very simple kinetic theory behind it. We know that most of our reservoirs don't have fluids that are kind of fit that description. Okay? So not only that, the fluids that we deal with are more complex, and they're also in more complex conditions. So I'm going to put them at very high temperatures, very high pressures. I have mentioned a couple of times already that basically your stress or the pressure you're at, it grows 23 megapascals per kilometer, and you're often working at 3 kilometers. That's huge. Okay. Also, your pressure grows about 23 Celsius degrees per kilometer, give or take, from whatever it was on the surface. So you're easily at 3 kilometers, you're going to easily hit 70 degrees or 69 degrees more than it's on the surface. So if you're in Texas, you're boiling in no time. Okay. So of course your fluids are exposed to very extreme conditions. Ideal gas law is probably not going to work very well. So we need something more complex. Now that something more complex is not as simple. Basically the way you derive these models is after doing a lot of experiments in the lab and then doing a little bit of curve fitting and figuring out which parameters do I need in there. So it can be a combination of theory and doing experiments. And Peng-Robinson equation states that pressure is equal to RT divided by this volume minus B minus A over V squared plus 2BV minus B squared. So I have a quadratic equation in V here divided by, and a linear equation in V divided by in first term. So this is now a more complex relationship. And my A and B, you can just, these are tabulated results, so you can find them. So you can just take them as constants. Those constants depend on the gas that you're dealing with. So if I actually put that my pressure is 50 bars and my temperature is 473 Kelvin, okay, I am in this particular case looking for f of v, that is this P minus this entire relationship equals to 0. So I'm kind of fitting it into this f of something is equal to 0. And this time I'm looking for a volume as well. Okay. So I'm looking for a volume such that these given pressure and temperature, I have this satisfied. So this is equal to 0. If it is, that same volume is satisfying this equation. Yeah? Now compare that to the previous one. Okay? If you had pressure and temperature given in the first one, what is my VI? If I have pressure, temperature given, R is a gas constant. So that's given too. So what is V? I. RT divided by P. I just plug in T and P into that, put it in, and I know what volume is. Can you give me that volume after I show you this? What is VI? I don't know. And I might or might not have a formula that gives me the volume. If I have a quadratic formula, great, there's a formula. But for anything more complex than quadratic formula, you don't know. So what do we do?
You iterate. Iterate.
Iterate somehow. So come up with a method and iterate and try to look, employ a computer to find it. What would be one relatively simple thing that you could explore, given that you have this? For different values of V, you can figure out what f of V is, right? So what could you do?
You have to start with an initial guess of VI using the ideal gas law.
Okay, you already know something about numerical methods, so sure. What else? What else can you do? Let's say that you don't have initial guess, but how do you explore this function? You could do trial and error. So what would be trial and error, which is taking different VIs and just seeing what f is and trying to see whether I'm going to get close to 0. What would be a consistent way to do that? A loop. And within the loop, we actually go and compute all of the values, and then I can do what with them? Plot. Okay? So I could do a graph of this function. I have a formula for the function. So a graphical way to solve this would be one way. Actually, I'm going to go through that model immediately. So basically, you get yourself some interval, and you just plot the function on that interval and see whether you're going to hit a 0 somewhere. Okay. Now, this is not, it's kind of maybe hard to know, like kind of know, is that, well, it's close to 15 somewhere here, right? So that's not necessarily the best way to do it, but it can give you an idea, and it's this trial and error. Now we're going to get to this idea. So basically the idea of all numerical methods is that you're going to start with a reasonable guess, okay? And then you will come up with a method that will, in a for loop or a while loop or some sort of loop, you will try to get closer to the actual solution, which is sort of a more consistent way to do trial and error. Okay? So that's what the topic will be. Let me actually give some more examples. This is example of a falling parachutist. Okay? So I am wondering what is, so typically I know per Newton law that force is equal mass to acceleration times acceleration. What are the forces in this business of falling from the sky? What forces do I have acting on me?
Gravity and drag.
Gravity. So there's gravity pulling me down, but then there's resistance to it, which is essentially drag from my surface going through the air. Okay, air is resisting my movement, so there is some drag to that movement, and that resistance, or the force acting on me because of that, depends on the shape of my body and the speed that I'm traveling with. Okay. So the way we formulate that, okay, is that there is a coefficient C, which is called drag coefficient, okay, times V. Okay. And V is my velocity. So basically gravity is pulling me down and the resisting force is away from that. Okay. And that is equal to m dv dt, and I could actually integrate this to get that this is what my velocity is in terms of c. Okay. Now, it's often that this drag coefficient is something that I'm looking for. Why? So the way an engineer would think about this problem, it's an engineer that is designing the parachute, or an engineer that is designing some other vehicle that is moving. So those could be airplanes, cars, and so forth. And they're trying to minimize the drag. Okay. Here we're actually trying to maximize the drag. Right? So this whole parachute has much more of a drag for its mass than I do. So it's going to stop me from falling, and I'm going to find this balance where I'm kind of just like floating down at a constant speed. Okay. So if I'm trying to design a parachute, okay, I'm trying to look for parachutes that have sort of an optimal C, which is where it's helpful to have a function that is basically relating velocity. If I'm experimenting velocity, I can measure. So from all of the measurements of the velocity with this particular parachute, I can see which C is actually fitting this. So basically, then I'm looking for C such that I'm just going to rearrange this and I'm going to formulate it as f of C is equal to 0. Again, so that we can use the methods we're going to talk about. So from the design perspective, you're trying to find and optimize these drag coefficients because you're designing it. Well, as petroleum engineering students, you're probably not going to design a parachute, but it could be a different problem where you're trying to. There is drag. Okay, let's find out drag in petroleum engineering. So if you have propellant particles that are injected to prop fractures open and keep them open at stress, basically there's drag. They're moving through the fluid, and because of their velocity through the fluid, there's quite a bit of drag force. So you will have a propellant particle. There's gravity on it. There's fluid carrying it, and then there's resistance to that fluid carrying it, which is drag. And you might still want to know what is your drag coefficient on that particle and how to optimize. In this case, you would probably be optimizing propellant particle. Spherical shape is pretty good for predicting things in porous media, but you would probably be optimizing fluid carrying it. Okay? And fluid viscosity plays a role in the drag. So you can typically work with different fluids and see, do they have enough viscosity to carry propellant? Okay. So there could be basically a problem like this as well in petroleum engineering. Now, the one we know really well is a quadratic equation. So if I have just a general quadratic equation, I have my solution immediately. But that's not always the case. Most of the problems, just like the 3 problems that I mentioned as example, do not have really an analytical formula that gives me a solution. So I have to look for it. And this is where we find approximate technique. So we will never be precisely finding the root, but we will get close to it enough. Okay? So my root finding techniques, there will be a number of them. First section will be so-called bracketing methods, graphical bisection and false position. Those are in chapter 5 in the textbook. And then there's open methods, fixed point iteration, Newton Raphson and secant. Those are sort of most popular ones, especially Newton Raphson. And then those are covered in chapter 6 in the textbook. There's a whole separate set of, yes?
Are these going to be in exams?
No. So exam is lectures 1 through 4. And I've covered that already today. We're not doing the review because we're doing it on Monday, and my schedule cannot allow for 2 class reviews. So we're getting, and also I do have to give you a week to sort of process the information. I can't ask you, I don't want to test you on this on Monday since we just introduced it. So polynomials, we will not go into the details, but polynomials are so common and they have a certain structure to them that allows designing methods that are specifically good for them. So that's a whole, there are 2 common methods for polynomials. We will not go into the details here. Basically, what you need to know about root finding, you will get from the methods that we will cover. You can always, there are always new methods coming up in any problem. Partially because no method works perfectly for all of the cases. So at some point for the basics you need to learn a number of methods and then just expect that as you go through you will improve on them and learn on your own some different methods. Okay? So again, we will focus on bracketing and open methods. Okay. So graphical method I already mentioned. So here is one of those examples that we had that was nonlinear, so I don't know the solution. I don't know C for which this equation here is equal to 0. But maybe I could just plot the points. So let's do that, okay? And this is your partial review for the exam as well. So let's plot on 0 to 20, let's plot this function. I'm going to give you a minute before I start working on it. Whoa. Yes, 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 yes. So this is my f of c. How's this? A little easier to see. I want both windows.
You want us to equate it to 0?
I want to plot a range of values, or this f between 0 and 20. So I know that plot function needs explicit points where I plot, right? So since these are points that are c and f of c, I first have to give myself a range of c's. I could just do 20 or 21 of them, right? I could refine my plot a little. I could use a linspace as well. This is already a review of plotting for exam. So what does linspace 0, 20 do?
Gives you 100 points between 0 and 20 on a line.
So by default, I'm going to get 100 points. If I want to change that, I need to give it one more parameter. So they're going to be between 0 and 20. So if I want 50 of them, I could do this, right? So what are the input parameters for linspace function? What are input parameters for this linspace function? All of the values that I put in, give to the function, 0, 20, 50, are my input parameters, and I have to separate them by comma, right? And the brackets type that I use are round brackets. What is an output parameter for function linspace? in the way I, right, and how am I calling it? C. Do I have to call it C? Can I call it something else? I wrote C equals to linspace of 0, 20, 50. Linspace is a function. I'm reviewing functions. So I could have any name. There are some restrictions on the name. I shouldn't start with like exclamation points or anything funky like that. Okay? So basically this is my function. Now this function is kind of built in, so I don't know much about it. I can do help and then only MATLAB gives me information on how it works. But there is an M file somewhere that basically has input and output parameters defined. All right, so let's, which way do you like better? This one or this one for creating C?
I just have a question. Are those equivalent? Do those like give you the same thing?
Not, well, I don't know that there are 50 on them in the first one. There is 40-ish. So they're different in that sense. So here I control the number of them, and here I control the spacing. And depending on the situation, you might want to control one or the other. For plotting, it's fine either way. Okay? So, your choice. So which one do you like better? First one. All right, we're gonna leave first one. So now I have my range here of C's, and I need to create equivalent F of C's. And here I want to do it using vectorization and without vectorization. What is vectorization? Here we go. We have a review for the test today. So if I'm using for loop, that's without vectorization. I just go value, C by C value, and I create my vector of F values. So let's actually do that first. So I'm going to say for I is 1 through length of C. That way I will definitely go through all of the C. Now C of I, at every I here as I'm walking through my array C, C of I is the current value I'm working with. And I want to create a corresponding F value. So I'm going to refer to that F value as F of I. Okay. And it's this funky function I'm going to so not C, but now C of I. I'm currently working with C of I. And then times. I'm old school. I do like putting a whole lot of brackets just in case. And then 1 minus. Exponential function is exp. I'm using a built-in function. Again, I have to do C of I here. And then minus 40. Okay. I'm going to execute this just to I saved my, so I'm just going to execute this MATLAB saying here, invalid syntax, I have a typo somewhere. So this is division times 1 minus, putting enough spaces, this is now debugging, essentially putting enough spaces so it's clearly written. Now my only complaint, or the complaint that MATLAB has, is that F is changing with the size. So the way I can prevent this I'll just say f is zeros of size of c. So I'm creating the array that has the same number of elements as c. And that way I'm letting MATLAB know, okay, this is the memory you need coming in. Stop complaining. And it did. Yes?
Even if you don't put that second line where you put f is 0.
It's still gonna, MATLAB is nice enough that it's gonna execute. Some other programming environments might not be.
Is that initializing?
Yes, so that's initializing my f. And it's a good programming practice. All right, so now I computed it. Let me just run to see that I got something. Well, C and F are showing up here. My quick check is you can actually look at this and see the values, whether they correct. I have a problem with the 0 because I'm dividing with a 0. So this is the first, this is now debugging part. I open my F and I see another number because it doesn't, yes, I ran it just to test. So it doesn't really work well with 0, obviously because I'm dividing by it. So I'm just going to get away from it. So now when I look, now it looks okay. All right. How do I plot this? Plot. CF. The simplest form is CF. Okay. So this is my function. How do I visually see where my intersection with the 0 is? How could I help myself to see that?
You could do grid on.
Hmm?
You could do grid on.
Grid on? Okay, yes, that's not what I'm thought of, but yeah, that works. So grid on actually gives me, typically 0 will be there, so this is where my solution is. I could also literally introduce a line. How would I plot a line of 0 line? Z is zeros of size of C. Okay. So I'm going to put this all in my, okay. And then I could say, hold on, plot C, Z. Let's execute that. I'm going to close this. And now I have 2 lines. Is everybody clear on what I did here? So now I can pretty much visually inspect. With my zooming tool. Okay. So I can see that the solution is here somewhere close to 14.8. And this is, I could also get grid on into here and get closest. But I'm kind of like just tapping around my values, right? I could examine these f of c's. I do have array, so I can actually get within which cell do I find a 0. So it's not very, it's more visual than it's actually getting a hold of the actual value.
Professor.
Mm-hmm.
So this isn't very accurate, but can you use that pressure tool underneath the desktop?
To find the point, yes. So you could do this. There's a way.
I was talking about icon. Like it's
Which one?
Desktop, the yellow one.
This one? Underneath the desktop.
Yeah, you clicked on it.
This one?
Yeah.
Possibly, and I don't even know. But yes, there's a lot of visuals. So how do I? So essentially, MATLAB plotted this value. So yes, MATLAB can return you like what is the closest point it is plotting to that group. Okay, so that's how you would find it.
Okay.
a little more accurate. But it's still a little bit of, nevertheless, graphical portion is very important in guiding you in general. So do not disregard this as a method. Now, just before I move on, I would like to address, now this is without vectorization. I have to use for loop. How would I actually compute this in one go? F. Copy this line. How would I operate on the entire array C all at once? That's called vectorization. Little dot, where does this little dot go? Right after this. So basically, instead of dividing, I say dot divide, and then it's going to do element by element business. And also dot times, so it's going to multiply element by element. This will actually be just fine. Exponential function will be vectorized automatically. So let's try to do that. Okay. And I'm doing it outside just to plot C. Okay. See whether I'm going to do the same thing. I got something slightly different, eh? Ah! What is my error? Debugging. So which C of I did it use? No. It had it went through the loop just before this. So it had the last I in memory. You can actually see it here, it's 40. So here it used C of I. Okay. This is what I mean when I say nobody's immune to making errors. You're going to make them all the time. And here it recovered just fine. What does computer know that I didn't want to use C of I? For all it cares, that's what I meant to do. Okay. So if I run it now, I'm going to pretty much get the same plot. Clear? What is vectorization versus not? Okay. Yes?
Did you run it as a script file?
Yes, I ran it as a script file, not as a function. I don't have, what do I need to have for a function? I would have to have, so let's do that. That's a review for the test as well. Okay. What do you want to be output? Maybe F should be output in that case. So my output parameter F, okay, is, I have to call it now roots parachutist. Okay. If I leave it like this, do I have input parameters? No, and that's fine. I could have it that way. In that case, I'm counting on creating C as an input, and possibly I should then give it as an output. Okay. Or I could actually make this function like this. So I provide C as an input parameter and F as a result or output parameter, in which case I would have to create C first and then execute functions. So how would I execute this function from the command line? If I now just call function like this, the way I was calling the script, that doesn't work because I didn't provide input. Okay? So now I have to provide input because that's how I define the function. Second thing, my F will not be remembered unless I capture it from the outside. So in this case, I'm going to store, maybe I can do it as an F1. Okay? Whoa. Save. Did I save things? I didn't save apparently. Ah, what did I miss here? Nobody said anything. Okay? And now I got my F back. Yeah? Questions about this before we wrap up? All right. I have office hours at 2.